Hi, I'm Maria. I'm here with Cheyenne, John, Glenn, and Sarnice, and we're going to be talking about radical cystectomies.
So our need statement is a way to enable patients to urinate voluntarily and maintain continence after cystectomy. Now let's move on to the disease state analysis. Starting with the anatomy and physiology, the urinary system is comprised of two kidneys, two ureters, and the renal pelvis, the bladder, and the urethra. In the picture to the right, you can see how the organs lie in the body. The urinary system has several main functions, and that includes removing waste products from the body, balancing fluids, balancing electrolytes, releasing hormones to control blood pressure and red blood cell production, and helping with bone health by controlling calcium and phosphorus levels. All these functions are carried out by producing and excreting urine from the body. Moving on to the pathophysiology. Bladder cancer is a fast-spreading cancer that can be lethal if not treated quickly. Radical cystectomies are performed if the cancer cannot be stopped from spreading. When a radical cystectomy is performed, the patient will no longer have a bladder and therefore no way to store urine being produced by the body. With no way to store urine, the body will not be able to carry out the urinary system's normal functions, so the bladder must be replaced with another way to store urine after a radical cystectomy. Typically, many symptoms that patients suffering with bladder cancer show are like symptoms of other diseases, making bladder cancer difficult to diagnose. Some symptoms include burning when urinating, frequent urination, and blood in urine. If misdiagnosed, patients can sometimes end up going a year or more without getting the right diagnosis, and that gives the cancer more time to progress to later and more fatal stages. The disease state analysis continued. In terms of clinical outcomes, if bladder cancer is not detected early, a last resort to stop the cancer from spreading is the removal of the bladder by a radical cystectomy. Usually, a radical cystectomy will stop the cancer from spreading, but as mentioned before, the bladder must now be replaced with a different means of storing the urine. Removing the bladder can sometimes lead to another whole slew of challenges and complications. For some statistics about bladder cancer is the sixth most common cancer in men, and there are about 500,000 active cases worldwide. Most cases of bladder cancer occur in patients over the age of 55 as well. Some risks linked to bladder cancer include smoking, a family history, exposure to dangerous chemicals, drinking water contaminated with arsenic, and chronic UTIs. As for the economic impact that bladder cancer has, medical expenditures are expected to rise over $5 billion in 2020 in the US alone. This number is most likely significantly higher worldwide because the US isn't even in the top 10 countries with the highest rate of bladder cancer. The top three countries in 2018 were Lebanon, Greece, and Denmark.
So with the existing solution landscape, as of right now, there are only two existing solutions following a radical cystectomy procedure. The first solution is the ileal conduit and stoma pouch, which can be seen in the picture on the left. In this solution, the surgeon uses a piece of the small intestine to create a tube that attaches to the ureters connecting to the kidneys to an opening in the abdominal wall. Urine continuously flows from the opening into the stoma, which is a collection bag that sticks to the abdomen. Once the bag is full, it needs to be manually drained. The second solution is the neobladder, which can be seen in the picture on the right. In this solution, the surgeon forms a new bladder from pieces of the small intestine and places it back into the body where the original bladder was located. One end of the neobladder is connected to the ureters to allow urine to drain from the kidneys continuously, and the other is connected to the urethra to allow urine to exit the body. Problems with the current solutions. With both current solutions, the small intestine is used. If any of the small intestine is removed, metabolic complications can arise within the patient. This can include altered bowel function, malabsorption of food, acid-base balance problems, electrolyte abnormalities, bone demineralization, formation of calculi, renal and hepatic problems, and impaired drug metabolism. For the ileal conduit, another problem is the practicality and comfortability of it. Having urine continuously flowing into a pouch attached to your abdomen can be uncomfortable and it could start to smell bad. On top of that, having to manually drain the pouch frequently can be a burden on the patient. Lastly, it can lead to other mental health problems for the patient because having a bag of urine attached to the body may be embarrassing for some people, and having to deal with that embarrassment regularly can be a lot for someone to handle. For the neobladder, another problem is that the surgery takes twice as long to perform, which makes it more expensive and riskier. Being that the surgery is longer, it may not be feasible for a surgeon to perform this procedure if they do not think the patient can handle it. Once a neobladder is in, the patient must drain it every 3 to 4 hours to prevent it from stretching. This could be a problem if there is nowhere for the patient to drain it. Lastly, the patient may need to learn how to put a catheter on their own to relieve pressure if urinary retention starts to occur.
So the next thing we did was stakeholders analysis, and we divided our stakeholders into two: influencers and decision makers, based on the impact of their decision in our design. In the influencers, we included patients, physicians, and facilities, because although patients are the ones that ultimately pay for our design, their decision is highly influenced by their physicians, especially when it's a new device that's coming into the business. And also the physicians, their decision doesn't, although it's influential, it doesn't, we don't expect it to influence our design in any way, because whether they believe it or not, as long as we got the approval we need, we can still market the device. And also facilities, the same reasoning goes behind it. Although their decision really matters, their influence in the design or in the marketing is not crucial. The decision makers are the payers, which could be the insurance companies and the out-of-pocket payers, but the out-of-pocket payers would not be considered that influential because they're not a lot in number. But for the insurance companies, they will have to create their own code, and they will have to make sure, we'll have to make sure we get that before we can even market it to any facilities. In the health and human services, we have two entities, the FDA and HIPAA, and both of their decisions will directly influence our marketing, because we can't market without FDA approval, which we need a PMA or a pre-market approval for. And HIPAA, we have to make sure when we do our clinical trials, we'll have to make sure our patients' privacy is kept, and we have to have the clear guidelines to be approved by HIPAA. Next slide. So the next thing we did were the market analysis in worldwide. There are at least 333,000 new cases that happen every year, and 20% or more of them get radical cystectomy, which means it's about 66,000 people. And of that, 25% will get the neobladder, and the 75% will get ileal conduit. Our target market is all the 66,600 people, because our solution is much cheaper and more comfortable than both the solutions out there. So we try to market throughout all those countries. But unfortunately, each country has their own different regulations for medical devices like ours, especially it being sorry, what do you call it? Sorry, can you pause it? So because our device is designed to be implanted, each country will have their own regulations, and each country could require different clinical trials being done. So we quickly figured out it would not be an ideal situation to go into the worldwide market before we do our analysis inside the US. We did our market analysis inside the United States, and there are about 81,000 new cases that happen every year. And from that, again, 25% will need to get their bladders removed eventually, which means about 20,000 people a year will go through the cystectomy. And out of that, 15 to 25% will get a neobladder. We could not get a specific number on that, like, but we got this information from a specific place, which is called Roswell Medical Centers. They said about 15 to 25% of their patients every year get a neobladder, and the rest will get ileal conduit. But because our solutions, both of the solutions out there cost more than $20,000, and our target price is between $15,000 to $20,000, we think we can market it to the whole 20,000 people to get our solution.
So when we were generating a new solution for patients who have had to have their bladder removed, we considered things for the solution that we thought it really needed and things that would be nice to include. The things we thought the device must have was it has to be elastic enough to handle stretch and still maintain its shape. It had to be biocompatible, durable enough to hold fluid, and the procedure must not involve removing part of the intestines like the current solutions do. The function of the bladder is to expand and to hold the fluid when it's full. And it also needs to release the fluid. So the device we come up with will need to be able to be elastic enough to fill with fluid and be able to contract without altering its shape. One problem with the neobladder is it usually ends up stretching after filled with fluid. So that's something our device we don't want to have. The material our device is made of needs to be biocompatible since it is going to be implanted into the body. We don't want the device to cause an immune reaction, which would cause the device to be rejected. The material needs to be able to withstand the acidity of urine that's going to pass through it. And the material needs to be made strong enough to hold fluids without rupturing, because if there was any leakage, it could cause infection and it could make it so the patients wouldn't be able to urinate. The device must also not include part of the intestine. The neobladder and the ileal conduit both incorporate the use of the small intestine, and it results in a lot of complications that we want to try to avoid with our design. But in addition to the must-haves, we also thought about ideas we thought would be nice for the device to have. It would benefit patients a lot to have more control of the release of fluids. No more need to empty a stoma bag or have a drainage hole in the body. No need to drain the bladder using a catheter. And a shorter procedure and recovery time would be nice for the patients too. So allowing patients more control over their bladder would give them a more practical way of living. According to the interviews we had, patients become really frustrated and embarrassed emptying and carrying a stoma bag around with them after the ileal conduit procedures. So it would be nice to eliminate the stoma bag in our new solution. With the neobladder procedure, it's a very common issue that they expand and stretch, so they can't be completely emptied. So the patients have to learn to put a catheter in themselves to drain the rest of the fluid. And we want to try to avoid these issues with our new solution. And lastly, it would be nice to provide the patients with the shorter procedure and recovery time, which would benefit both the doctor and the patient, causing them less stress after the surgery for patients and require less follow-up appointments.
So for the lead concept, when we were talking about it, we wanted to find a cheaper option than the neobladder and the tissue engineered bladder, which had been our other two ideas, were to modify the neobladder or to tissue engineer one. So with our new concept, which is just to make a biocompatible new bladder, it would allow for a cheaper option without having to go between those two. We would design it to be biocompatible, which there would be no issue of rejection with the biocompatible lining we would add to it. And it would yield less complications from the surgery than the neobladder would. Due to other issues, it could not be biocompatible with the neobladder. It can cause issues in the body. And also it would become a part of the person rather than just an addition into them. And it would also remove the need for a stoma and a catheterization procedure, which are very uncomfortable for the patient and they would have to live with it in their day-to-day life, which is definitely not ideal. We want a solution that will be ideal for a patient and the medical workers as well. So for our runner-ups, when we were discussing our top three, one of them was a tissue engineered bladder, which is very expensive. You would need a specific holding cell for it, basically just to keep it working until it would be implemented in the body, which can take a long time, and there might not be the space or time to do that, and it would cause us to maybe rent an area or need to buy the holding cell to keep it in. And then each bladder would require extra time to be ready for the procedure, as it would have to engineer itself into the bladder. And with modifying the neobladder, it was also an expensive solution, which we were trying to avoid the expensive cost for those who were out of pocket. And it would still require a stoma and a catheterization process, which again, we were trying to avoid, as it's very uncomfortable for the patient. And we want something that is best for them in the end. And it does yield complications within the surgery due to its risk of rejection and other possible issues that come with taking a part of an intestine and then having the stoma bag attached and such. So now we're going to talk about the key opportunities and risks.
Yes. So first, we conducted a patent research method. The goal of this is to simplify the search patentability and the public disclosure of similar solution to our idea. So following the textbook format, we identified 3 questions, which is what is the basic need being solved, what is the structure, and what is the function of the device. On the table to the right, we generated different simple key terms that we could input in the Google Patent software. And that once we were able to put these key terms, we identified the patents, and then we pasted word for word the key claims and things like that. So now into the second slide, we see simply a few main solution of the research of different patents that we found. We didn't find that a patent embedded an idea like ours, which is a synthetic bladder, but we did find that some identified different ways to treat urinary continence. So from this, we basically learned that we have to keep in mind that although they didn't make a bladder themselves, they did identify different mechanisms to take care of the urinary incontinence portion. Next slide. So first, for our regulatory fundamentals, we identified that because we first want to test the safety and the effectiveness for our device, we want to prove that to the FDA. And we went on the FDA website and we're not able to find any predicates of a synthetic bladder or a tissue engineered bladder or either modification to the neobladder. So then we were able to find that we would have to take on the PMA pathway because our device is high risk, it is implantable, and it doesn't have a predicate. So the PMA pathway that we chose is the modular, which is a quicker approval where we simply send the FDA some reports in a manner along a certain period of time in the calendar, and we get quicker approval for that. For the clinical study, our goal is to simply, because we're taking the PMA route, we have to do a clinical study to also prove that our solution can perform like the ileal conduit. So we plan to simply write a report explaining our design, our methods, and the results that we obtain. So we propose to have a bench test design with animal models where we would operate on those models to test the efficacy that they would be able to store the urine after the removal of the bladder and enable continence. And also test for sterilization and biocompatibility. Next. So with this reinforcement basics, our goal is to find how our device fits into the market for coding, for coverage, and payment. We identified that the primary payers are insurance companies, Our healthcare system is private and delivery system will be public. Also, the radical cystectomy will be done in a hospital settings performed by surgeons. And the device, our device, the bladder itself, it will not, our solution will not be available for testing prior to use by the hospital staff. Next. So from different research, we found the coatings, the different types of coating that are used for the ileal conduit and the neobladder. They are displayed on the table. And from this, we identified that our device will have to be regulated at a set price. And the reimbursement system for the United States amounts our reimbursement to around $20,000 to $30,000.
So then for our business model canvas, to deliver great attractive value of our service to customers that is compatible with strength and capacity of our company, as well as to refine the relationship with different prominent figures, we created a business model canvas chosen for innovation. Model is in the goal of optimizing many defining factors such as revenue, regulatory hurdles, margin structures, and more. The selected model we chose is to implement what we believe is the best approach at this stage of the development of our solution. Because we have a high cost device that is specialized in upholding a high function, it is attractive in regard to the ileal conduit as it reduces the need for the stoma, which brings discomfort, and the patients can obtain similar results to the neobladder without the high cost. Overall, our solution as an implantable device, as people worldwide are affected by bladder cancer, there's a great need to uphold the function of the bladder as well as the quality of life. Our margin structure is profitable as there is an increased need for cystectomy procedures. However, the device will require lots of sales investments as well as IP business. There is a large amount of testing and research that is needed to be done as it poses a great risk to the human body. We perceive the customer training required to use this innovation to be minimal, as the surgery will be performed by a surgeon in the field and the device itself mimics the natural process of urination. However, it is anticipated that because it's a high-risk medical device, it has to go through the PMA regulation pathway with the FDA, which will be time-consuming to conduct trials and to prepare reports. And then lastly, we will need a lot of funding to invest into technical developments, as well as being able to market and sell the device to hospitals and insurance companies.
So first, if you remembered earlier, we had identified three main living concepts, which are the neobladder, modifying it, the tissue engineering bladder, and the synthetic bladder. So we identified some design requirements just so that through this process, we could choose a final living concept. And from the way that we found that it is best of our interest, it is our best solution with the lowest risk to have a synthetic bladder. And this is what basically this table shows.
So for our questions, we were asked to discuss the process of innovating medical technologies, basically discussing the focus on identifying, inventing, and implementation phases. So within the medical device industry, there's always going to be a need for an improved device or a new one in general. So to confront that need, there are steps needed to be taken when ready to do so. Initially, you want to identify the issue at hand, whether it's a device already made but was found to have issues that should be dealt with, or trying to find a resolution for an issue at hand with no solution available yet. This can be through any form of brainstorming, talking to those within the medical industry to hear their side, etc. But before any process starts, identification is highly necessary. Once it is identified, the team does have to take the time to work through any possible issues that can come with potential ideas discussed to narrow down any that would cause more negative results than positive. By doing so, we can resolve it into a potential idea, building off that to make sure it covers all safety and mechanical bases. This will come with a lot of testing and research on different materials and functions, as each part will have its own several aspects to it to work through in order to fully create the device they are attempting to invent. After this long process, it does come down to finding a way to implement the idea into the medical field. This would make it available for patients to access it, making medical professionals want to use it, any way to get it into the system to become an option for those who need it. This comes with discussing the device with hospitals, advertising it, making it publicly known that the device is ready for use within surgeries, and to use this device rather than the ones that are already available.
Okay, so for the second question, we're asked to discuss the relevance of each phase: identifying, investing, and implementing. Maria already discussed the importance of them in a general setting, but for our specific device, we found these three phases to be very important. Like identifying the problem, we had so many other problems to choose from in any medical field, but we thought this problem it's never been addressed, and there are a lot of people that are suffering, and there are a lot of age groups included, and a lot of individuals affected with this, and identifying the problem was a long process, but it was worth it to work with because we got to learn a lot from this process. And inventing it it was also a challenging process because we needed to choose from not so many choices that are available already, and there was only almost one thing we could do, but because the person would not have a bladder, we needed to make a new bladder. That's technically what we were dealing with. But the invention process also was very helpful in addressing the issue. And the implementation process, we also figured out how it'd be very difficult to put it into the market and go through the approval process and go through the marketing. So we made sure these three phases were really important in our problem we were addressing.
Question 3, discuss one specific risk of your proposed medical device concept. Being that our proposed device will be a synthetic bladder, the synthetic material will be foreign to the body. This poses a risk because the body might try to attack the bladder, thinking that it is not supposed to be there. There are different ways that the body tries to get rid of foreign materials, which includes sending immune response cells to try and phagocytize or eat the foreign material, or walling the material off in scar tissue. Either way, the body attacking the synthetic bladder would be a risk because it could cause the bladder to not function properly, or it could even cause an infection in the patient that could lead to further complications.
Question 4, discuss one specific risk mitigation strategy to address the device concept risk discussed in 3. So as discussed earlier, one of our main risks is the possibility of rejection is very high when we implement the synthetic device. So to lower this risk and to address this risk identified, we would put a biosurface coating layer surrounding the implant itself, the synthetic bladder itself, so that when we implant it into the patient, it will decrease the risk of rejection to a minimum.
So then for question 5, we were asked to discuss the strengths of a UML BME student in participating in the process of innovating medical technologies. So for students like us participating in innovating medical technologies in school, it helps us learn the process and techniques required not only to build and design a device, but how it will function in the market. So being able to take our already acquired skills we've learned from class and walking through the process of what it takes to create a functioning medical device has helped us prepare for life after college, where we will be applying these strategies to our own jobs as biomedical engineers.
And then we just have our references here in both pages. And I just want to say thank you for taking the time to watch this video. And I hope you have a great day and happy holidays. I'm trying to stop the recording, but I can't.